Good evening, Lamai. Right, today we are going to discuss about the compound synthesis processes using the Benzene ring. Right? Okay, compound synthesis using the Benzene ring, right? Involving in the Benzene ring, right? That is the discussion today, right? Let's start this thing, right? So you can clearly see some chart is there, right? So here the benzene appears, and basically to benzene we can connect actually four groups directly to the benzene ring, right? In our syllabus, according to our syllabus, we can only connect four groups. Only four groups can be connected directly to the benzene ring by only a single step, right? Those are these four groups. Let's discuss about that thing and start the discussion, right? So basically, so if you need to connect a halide group, if you need to connect an halide group, it could be a bromine or it could be a chlorine. So if you need to connect a bromide group or a halide group, right? So what you need to do is you have to add some Br to connect. If you need to add some Br to connect to the ring and some Br to leave, right? So one of the Br will connect to the ring and the other Br will leave, right? So that the region you should add is the Br2. So you need to add the Br2, right? For one Br will connect to the ring and the other Br will leave. As this one leaves, that bond will connect to the ring. That is how the things will apply, right? So you need to copy the Br2, right? Br2, and you need to copy the catalyst Br2 with the catalyst, right? The catalyst is the anhydrous, right? FeBr3. The Br2 anhydrous FeBr3 catalyst should be used, right? Then one of the Br will connect and the other Br will leave, right? To this thing as well, what you need to do is with the group you need to connect, the alkyl group, you can add a halogen to leave. So the compound you have to add here to connect this group is CH3, CH2, Cl, CH3, CH2, Cl. The other Cl will leave while this section will connect with the ring, right? While the Cl leaves, right, that bond carrying carbon will connect to the benzene ring. So that you are able to connect an alkyl group to the benzene ring. So with this thing, you need to come up with the catalyst. Always you need to come up with the catalyst to connect the things to the benzene ring at once. Directly to connect to the things to the benzene ring, you need to come up with a catalyst as well, right? So the reagent and the catalyst both should be written. Without the catalyst, the reaction won't occur, right? So that is how you are supposed to, right, connect an alkyl group, to the ring, right? Then you can connect kind of a ketone group to your ring, benzene ring. To do so, what you need to do is just add the reagent contained in this section with a Cl to leave, right? So it is going to be CH3 C double bond O Cl to leave. As the Cl leaves, this carbon will connect with the ring to give you the ketone section to the ring, right? So again that should be added with the anhydrous AlCl3 catalyst, right? Okay. So then as the fourth route, we can come up with the NO2, right? You can connect some NO2 to the ring, right? So that NO2 is coming like this. The reagent is the concentrated HNO3. Right? So HNO3 is like this, no? HNO3 is like this, right? This is your HNO3, right? This is HNO3, no? So you have some H's as well, no? This is HNO3, right? Okay. So this group will leave while this NO2 section will connect to the ring. The NO2 section will connect to the ring while this group will leave. This is also a 7-neutron system like halogens, right? So this thing will leave while this bond will connect to the ring. right? So that is the concentration tree, the reagent, and you need to add this with the catalyst. The catalyst is actually concentrated H2SO4 at this instance. So those should be added with 50 Celsius temperature. So these are the 4 types of groups which we can connect to the ring, right? Directly, right? Okay. It is very clear what are the 4 types of groups. A halogen can be connected to the ring directly. An alkyl group can be connected to the ring directly. For that, you need to come up with that alkyl group, which you need to connect with the Cl. Then 100 ClCO3 is the catalyst there. And a ketone group can be connected to the ring directly. A ketone group can be connected to the ring directly. For that, with this ketone group, to leave some chlorine should be there. That is the compound, the reagent you should add to the benzene to connect that thing with a N100 ClCO2 catalyst. And to connect a NO2 group to the ring, you need to come up with the concentration of free and consider sulfuric as your catalyst, right? So only these 4 guys are, again I'm telling you, can be connected to the ring directly by just the one separation, right? Okay, let's examine more about this, right? So if you are to connect a halogen to the ring, a halogen to a ring, you can convert that halogen. You can convert that halogen to a MgBr, to a Grignard, by just adding magnesium dry ether. Just adding magnesium dry ether in dry ether medium. You can convert that so form halobenzene to a Grignard benzene, right? So the importance of this route is actually, if you add some acidic water, you can obtain the benzene ring again. Right? As this carbon is negative, as the Grignard section is connected, so as this carbon is negative, right? This negative carbon will attract the H plus here, leaving the Grignard, so that the ring becomes a benzene again. Right? That is what it happens. So if you are adding some D plus D2O, some heavy water, deuterium, right? D plus D2O, then what will happen? This negative carbon will attract this positive D plus to come up as a D here. So all the other 5 things are hydrogens with the ring, and you have a D here, specialty, some labeling, deuterium labeling, right? So that can be done by this reaction pathway if you are to add some D plus D2O to the benzene Grignard, right? Now that is all about the first pathway we had discussed, right? That is the bromination pathway. This process is called as a bromination. I'll write that thing as well. This process is called as a bromination or the halogenation. Right? Then let's discuss about the second pathway available for reactions with benzene. Right? The second pathway available. Right? That is referred to as the alkylation, connecting an alkyl section to your benzene ring. Alkylation pathway. Let's do the stuff. Let's discuss about that thing. With the alkylation, you can come up with this one, and that CH2CH3 group can be converted to the benzene carboxylic acid. The CH3CH2 group, the alkyl group, can be converted to the benzene carboxylic acid by adding some strong oxidizing agent. It could be the H plus KMnO4 or the H plus dichromate. By adding H plus KMnO4 or the dichromate, you can convert the alkyl group to C double bond OH group, right? That is the possibility with the alkylation pathway, right? So basically in benzene, right, this kind of a thing is there, right? In benzene ring, this kind of a very special reaction is there, right? So if you are starting with the benzene ring, if you are with a benzene ring, and if that with that ring, the connected carbon to the benzene is with a hydrogen 5 bond or oxygen or a 5 bond, at least one of those, at least one of hydrogen oxygen or 5 bond with the carbon connected to the benzene ring. If you are with this kind of a situation, then if you add H plus KMnO4, if you add H plus KMnO4 or the H plus dichromate, if you add the H plus KMnO4 or the H plus dichromate, what will happen is actually that carbon will convert to the benzoic acid. That carbon will convert to the benzoic acid. This is very special, nah? It's a very special situation with the benzene ring, right? So that will convert to the benzoic acid. It's a very special situation, right? Right? If you have a carbon connected to the ring, directly connected to the ring with one of these things. If you have a carbon directly connected to the benzene ring with one of these things, with at least one hydrogen, with at least one oxygen, or at least one 5 bond, right? If you add some strong oxidizing agent like acidic KMnO4 acetate dichromate, the ring will be converted to the benzoic acid, right? It's the benzoic acid. Benzoic acid, right? So that is the reaction occurring here. So this carbon is with such a situation, right? Some hydrogen is there, so it will convert to benzoic acid, right? Okay, let's discuss about the third pathway available with the benzene ring. The third pathway, right? What is that? It is referred to as the acylation. Acylation, right? So they are we are supposed to connect kind of a ketone group to the benzene ring. Kind of a ketone group is connected by adding a acid chloride with the anhydrous AlCl3 catalyst. So this ketone section also can be converted to the benzoic acid by adding the H plus KMnO4 or the H plus dichromate. By adding strong oxidizing agent, you can convert this ketone group as well to the benzoic acid, right? Ketone group as well to the benzoic acid, right? So this is the theory there, right? As this one is carrying some 5 bond as well as oxygen, this will also convert to the benzoic acid, right? Not only that, right? You can convert this stuff to the secondary alcohol as well. The ketones can be converted to secondary alcohols easily, no? So for that, you can come up with lithium aluminium hydride. In dry ether you need to add with the acidic makeup as well. And this thing could be done with the use of PCC. The secondary alcohols could be converted to the ketone with the same 2 R groups, right? With the addition of PCC, right? That is clear, no? Right. Then Lamai, this thing also can be done, no? This conversion also can be done. By just adding H plus KMnO4, right? H plus KMnO4 will do that thing as well. H plus KMnO4 or H plus dichromate, right? H plus dichromate. So the same logic here as well. You are with a carbon oxygen bond, no? Carbon hydrogen bond as well as a carbon oxygen bond, no? So definitely it will get oxidized to the carboxylic acid. In aliphatic conversions, right, secondary alcohols will stop at the ketone. Secondary alcohol will stop at ketone when you are add some oxidizing agent, the H plus KMnO4 or the dichromate. But in aromatic chemistry, the secondary alcohols as well will convert to the benzoic acid due to this reaction, right? Okay, right. Next stuff. what else? So basically we'll move towards the next things, right? So this conversion also can be done with the use of Clemmensen reduction, right? The Clemmensen reductions means the aldehydes and ketones will convert to the alkenes. No? That can be also done, right, with the benzene ring as well. Right, let's discuss about the third route available here. Sorry, fourth route. The fourth route available here. It is referred to as the nitration, the benzene nitration route. Connecting an NO2 group to the benzene ring is referred to as the nitration, benzene nitration route, right? That is the fourth route we are going to discuss, right? Let's examine this, the fourth route, right? So you can connect kind of a NO2 group to the ring by adding HNO3 concentrated with the H2SO4 catalyst at 50 Celsius, and you can convert this NO2 to a NH2 by doing a reduction. Getting rid of oxygens and adding some hydrogens is actually referred to as a reduction. So reductions can be done with reducing agents. Metals are known as good reducing agents, so that if you add some tin with conc HCl with an acidic medium, tin with conc HCl and some NaOH and heating, if you are to add this reagent, this NO2 will be converted to the NH2. This NO2 will be converted to the NH2, right? And this is referred to as the aniline, very important reagent in our chemistry, and this is referred to as the aniline, right? This is referred to as the aniline. So make that name, aniline, right? That is aniline. So that aniline, the benzene NH2, the aniline can be converted to the OH here by adding NaNO2HCl. So normally NaNO2HCl is the reagent we use to convert the NH2 group to a OH. NaNO2HCl, the HNO2, is the reagent we use to convert that NH2 groups to OHs, right? So that reagent could be added here to convert the NH2 group to OH. The reagent is what? NaNO2HCl. Na2HCl. So this special compound is referred to as the phenol. The benzene with OH group is referred to as the phenol. You had the aniline, now this is the phenol. This is the aniline and this is the phenol, right? So if you are to add the same reagent, to aniline but with a lower temperature, if you add the same reagent NaNO2HCl but with a very low temperature, with 0 to 5 Celsius, if you add the same reagent with 0 to 5 Celsius, what will happen is this NH2 will convert to N2Cl. This NH2 will be converted to N2Cl, and this compound is known as the diazonium salt. Very important compound in our chemistry, referred to as diazonium salt. Diazonium salt, referred to as diazonium salt, right? So that can be made by adding the same Na2HCl but with some 0 to 5 Celsius with very minimum temperature. The temperature should be clearly mentioned by diazonium salt, 0 to 5 Celsius. Here basically it is the temperature is greater than 10 Celsius. The room temperature will give you the phenol. If you are to add the same reagent at very low temperature, the aniline will produce the diazonium salt, right? So before going towards the reactions involved in the we'll discuss about the reactions first of all involved in diazonium salt. Basically, this diazonium salt is carrying some positive carbon. Here. Diazonium salt is carrying some positive carbon here because of the electrons are attracted towards the nitrogen, right? Which is more negative. This carbon is more positive. So towards that, nucleophiles could attack. Nucleophiles could attack, right? So as this positive carbon is there towards this, nucleophiles could attack. So we can connect the Cn minus Cn by a Cn minus nucleophile. We can connect the Cl minus Cl, Br and I from X minus nucleophiles, right? So if you add those nucleophiles, we can add those nucleophiles to the diazonium ring, right? So let's do this stuff. To convert the Cn, right, what you need to add is the Cn minus nucleophile, right? What you need to supply is the Cn minus nucleophile. So that can be supplied by CuCn. So basically Cn minus is supplied with Cu plus cation, right? Here the Cu plus cation is behaving as a catalyst, right? These reactions are referred to as Sand-Meyer reactions. With the use of Cu plus catalyst, the reactions are done. So Sand-Meyer reactions. So using the Cn minus nucleophile and the Cu plus catalyst, right? So to do this thing, what we need to come with is CuBr or CuCl, CuCl or CuBr. To add this nucleophile, the Cl or the Br, you can come up with the Br minus with the Cl minus, right? As the catalyst, Cu plus is used. The Sand-Meyer reactions, at which they are, right? That name is indicated in your note, right? And this one, to add some iodine to the ring, just Ki is enough. No Sand-Meyer is needed. Just Ki is enough to give that I minus nucleophile to the ring, right? With the diazonium salt as well, you can produce the benzene again. For that, what you need to add is H3PO2. If you add H3PO2 and heat, you will get the benzene from the diazonium salt. Just some hydrogen will connect, leaving this part, right? So then the other thing as well, the diazonium salts can be converted to phenol as well, right? Phenol as well by just adding some water and heating. Right? Diazonates can be converted to phenol as well, but just adding some water and heat. Water will supply the OH group. H and OH, water means H and OH, that OH minus nucleophile at the water will supply the OH group by releasing this N2 section, right? When diazonium salts are participating to produce these things, always the N2 gas will be released. Just mark that thing as well. Always the N2 gas will be released by these reactions involving diazonium salt. When the nucleophile connects to the ring, this diazonium section, the N2 will be released, right? You can clearly see the N2 is appearing, right? So N2 gas will release, right now. So this reaction is very straightforward. Converting a Cn to C double bond OH is very straightforward. Just adding H plus H2 acidic water will convert your Cns to C double bond OH. That is clear. And we'll discuss about this thing as well, right? These two reactions, very special reactions are there. So basically, these anilines and phenols are very special. Phenols are very special, right? The specialty of these anilines and phenols are actually, those are referred to as very active rings. That means electron rich rings. These rings are very electron rich, not like normal benzene, but the aniline and phenol rings are very electron rich. Why I am saying so? The point is this, So when it comes to aniline and phenol, those rings are very electron rich. Why is that? Because in aniline as well as phenols, this lone pair will be donated to the ring like this. So lone pair will be donated to the ring. So that in aniline, these positions, in this position, we get a negative charge. See, this electron is coming towards here. So that position will get a negative charge like this. See, this ring, you get a negative charge here due to this electron transition, right? Not only that place, but when these electrons are coming towards here, this place also gets some negative charge. See, the place directly opposite to the ring, directly opposite to the NH2 will get some negative charge. See, not only that position, but also when these two guys are coming here, this position will also with some negative charge. This kind of special thing appearing with the aniline and benzene rings. Right? You see the two nearest positions here as well as here, the two nearest positions in NH2 as well as the opposite, directly opposite position to the NH2 will get some negative charge, so that the electrophiles, the E pluses, will keenly attract towards these positions, the two nearest positions, two adjacent positions to the nitrogen containing carbon, and the directly opposite position of the nitrogen containing carbon will attract the electrophiles heavily, so that these are referred to as very electron rich rings, and electrophiles will be very keen to attract towards these three positions of aniline as well as phenol. With the phenol as well, the same kind of thing will appear, right? With the phenol as well, see, this lone pair is there, right? So same kind of thing will appear with the phenol, right? Because of the lone pairs available in those, right? So with aniline and phenol, only with the addition of Br2, OX2, Cl2, you could be able to, right, come up with these kind of tribromo products, very activated rings. So just adding Br2 will give you tribromo products, with phenol as well will give you tribromo products. Right, by just adding Br2, even without catalyst. If you add Cl2, you will get trichloro products, this thing as well, even without the catalyst, right? To add some halogen to the benzene ring, right, you need a catalyst, but that catalyst is not needed to add the same bromines to the phenol ring or the aniline ring, because those rings are considered as very electron rich rings, and to those positions, these three positions, one after the other, the BRs, the halogens will be added, right? These are referred to as tribromo products, right? These are referred to as 2,4,6 tribromo products. This is 2,4,6 tribromo aniline. This is 2,4,6 tribromo phenol, right? Okay. So actually these are the major, right, reactions involved in the benzene ring, right? These are the major reactions involved in the benzene ring. Clear, no? Right? So you should know all of these reactions which are originating from only four pathways. Right now? So let's do one or two conversions regarding this note, right? You can clearly complete this stuff, and after that we can do one or two conversions using this note, right? Okay, just complete the stuff. Right, let's do the two things first of all. Right, see, this is a carboxylic acid. So to the benzene ring, some carbon is connected. So surely you need to use the second pathway 1 or pathway 2 or pathway 3. The alkylation or the acylation pathways should be used to come up with this section, right? Because with the first pathway you are starting with bromine and MgBr and those stuff. No carbon involvement with the first pathway. With the fourth pathway, right, some polar things are involving, carbon polar things. Because first unit will come up with the nitration, the NO2 stuff. So with that, with the benzene ring, some carbon polar bonds are made with the fourth pathway. The NO2s, NH2s, right, then the OHs, ultimately that halogens, right? Some polar pathways. The first one and the fourth one are polar pathways. To form benzene carbon bonds, carbon with the benzene, that kind of bonds, you need to follow the alkylation or the acylation pathways, right? Okay, so and we know this benzoic can be formed by that special reaction, no? The benzoic can be formed by that special reaction. This is known, right? So if you are with some carbon which is with at least one hydrogen, oxygen or a 5 bond, we know if you add some H plus KMnO4 OH plus dichromate to this thing, we know the product is going to be the benzoic acid. Product is going to be the benzoic acid, no? We know this stuff, no? Right? It's known stuff, no? So the benzoic acid can be formed by any of these things. If you are with a hydrogen, oxygen or a 5 bond at your carbon. So now this is very clear then. So what we need to do is just do a alkylation, right, which will give you a alkyl group there, So even you can do this kind of alkylation, no worries. No need to come up with just one carbon. Even though you are with 1000 carbons here, if you are right okay with this requirement, if you are fulfilling this requirement, even with the 1000 carbons here afterwards, right, still you get the benzoic acid, right? Still you get the benzoic acid, right? So this can be done with the use of CH3CH2, Cl, right? CH3CH2Cl, right? With some anhydrous AlCl3. If you add some CH3CH2Cl with the anhydrous AlCl3, this section will connect, leaving the Cl, this section will be connected with this carbon. After that, you can do this conversion. By just supplying H plus KMnO4 there. Right now? Okay. So what about this? See? Again, to the ring, a carbon is connected. So first we need to come up with a alkylation, no acylation. Right? Alkylation, no acylation. Right? Let's think of that. Right? So this is kind of a alcohol. Actually, it's a secondary alcohol. See, with this carbon, you are with 2R groups. So it is better to come up with a ketone first of all. The secondary alcohols can be made by ketones. So I prefer to go through the acylation pathway here, the ketone pathway here, rather than going with alkylation pathway, the alkane pathway. Right? Let's go with the ketone pathway. Right? Then it will be easy to form that compound. See? It's there. So we'll connect this one. Right? So that can be done by adding CH3COCl. This thing will be connected by leaving this thing with the anhydrous AlCl3, the catalyst. Now this is okay. So now what we need to do is just what? Just converting this carbon to the alcohol. That is simple step, right? Which we have learned with the note number 2. Converting a ketone to alcohol is just can be done by adding lithium aluminium hydride. in dry ether. Second step is just H plus H2O. Right now, so this is what we can do, right, to do this kind of a conversion. Right now, okay, let's do few more stuff. Right, see the number 3. So you have provided this thing. And they have asked you to come up with this. Right, okay, see what can be done to do this stuff. So basically, again, some carbon is connected. So better to come up with alkylation or acylation. So carbon pathways, right? So we know is kind of aldehyde. So aldehydes can be made with primary alcohols as well as carboxylic acids. So we could think of a carboxylic acid formation. So if we can come up with the carboxylic acid, the benzoic acid like this, we can come up with the aldehyde by the note number 2. The carboxylic acids, aldehydes and the primary alcohols are with some relationship, right? Okay, see what can be done. So basically you can first perform a alkylation or kind of a acylation, no worries, right? So both will lead you to the carboxylic acid, no? So I'll come up with the acylation somehow, no worries. So this could be done with the use of what? With the use of a CH3COCl. So this section will be connected with anhydrous AlCl3. Right? Then ketones can't be converted to the aldehydes, right? Ketones are carrying 2 R groups, but the aldehydes are carrying only just 1 R group. So first of all, you need to come towards 1 R groups. But in benzene chemistry, basically the 2 R group carrying ketones can be converted to the benzoic acid. Acid, which will carry only 1 R group through this reaction. Right? So now we are happy. So now you have a carboxylic acid. So now you know what to do. The carboxylic acid can be converted to aldehydes by just first converting this into primary alcohol, then the aldehyde, note number 2, right? So just convert this into primary alcohol, the CH2OH, that can be converted to the aldehyde by adding PCC. This conversion can be done by lithium aluminium hydride. Right now, so this is how we are supposed to do this kind of a conversion. Right now, right. First do this one. So you are supposed to add this alkyl section. Supposed to add that alkyl section. So what you need to add there? So to add that alkyl section, First write that thing. CH, CH3, CH3. First write that thing. And instead of the benzene thing, just write the halogen left. Halogen left. Right now, this group will be connected by leaving this halogen. For that bond, the benzene will be connected. That is how you are supposed to come up with the compound here. So this is alkylation. It should be done with the anhydrous AlCl3 catalyst. Right now? Okay. Let's do this one. Do this stuff. Right? So you are supposed to connect this group to the ring just by a single step reaction. So just write that group which you are supposed to connect. Right? So to that thing, to leave, just add an halogen. So this group will be connected by leaving the halogen. Instead of the halogen, the benzene will connect there. Right now? So with the anhydrous AlCl3, you can add the stuff. Always a catalyst is needed. No? Right now? Let's discuss about this thing. This one. Right? What we can do? What we can do? So clearly we see that Na-N2HCl is there. So Na-N2HCl is used normally to convert the NH2 group to the OH, or in the benzene cases, it could be to the diazonin salt as well. Right? That depends on the temperature here used. It depends on temperature used. So basically 0 to 5 temperature. That means it is about the diazonin salt, not here. If you are using the Na-N2HCl at the normal temperature, it will give you the phenol, the OHC. But at this special temperature, 0 to 5 very low temperature, it will give you the diazonin salt. So definitely with this reaction, right, the aniline and the diazonin salt, the two guys are involved. Aniline and diazonin salt, the two guys are involved. Right? So we'll start with that. That is the best place to let's start up with to solve this problem. Right? So with Na-N2HCl, there is a characteristic reagent used with the NH2s, right? That will convert the NH2 to OH at the normal temperature, but with the special temperature with the benzene ring, you can come up with the diazonin salt. Right now? Okay. Then let's complete the next steps, right? Okay. So we need to have some more stuff, right? Sorry for that. One more step should be there, right? This is that. One more step should be there, right? With the conversion. Next one. So let's complete this one. Let's complete this stuff, right? So diazonin salts can be converted to cyanides by the Sand-Meyer reactions. So just add CuCN. So the Cn minus thing will connect with the carbon, leaving the N2. Right? So here the NH2 things are formed via nitration. Via the fourth step, the NH2 things are there. So the nitration. So benzene can be nitrated with the use of conc HNO3 conc H2SO4 at 50 Celsius. Right now? Finally, we can complete this stuff. There is a reduction to convert the NO2 to NH2, that is reducing agent tin with conc HCl. Secondly, you need to come up with NaOH and heat. This is how we are supposed to complete that problem. Right? Okay, no? Right. Just complete the stuff. Let's do this one as well, the final question. Starting up with this. This kind of stuff. Right? See how we can come up with this kind of stuff. Right? Let's try to complete. Okay. This kind of a thing, right? One after the other, the bromines are applied. One after the other, the bromines are connected. This is possible via aniline or phenol. Right? So that definitely, if you had an aniline section here or a phenol section here, this is possible. Right? So what has happened? What has happened here? Right? Basically, definitely the three bromines are connected when the NH2OH was there, right? Then they have get rid of this section. Then they have get rid of this section. Right? So basically, right, at this point, we had NH2O OH there. At this point, when the BRs are connected, BRs can be connected like this only when NH2OH is available there, right? So at this stage, this could be there. And with this step, they have get rid of this NH2OH. They have get rid of that NH2OH, right? So that can be done actually by only with the OHs, NH2s. So with the reaction scheme, you clearly see the OH groups can't be released from the ring. You can't get rid of OH groups from the ring. But the NH2 groups can be get rid of from the ring by what? By adding H3PO2 and heating. The H3PO2 and heating will get rid of your N2Cl. which is actually can be produced by NH2s. Which actually can be produced by NH2s. Clear, no? We can't get rid of OHs, but we can get rid of NH2s via N2Cls. We can convert the NH2s to N2Cls that can be get rid of by the H3PO2. Right now? So this could be the conversion of this thing. That means NaNO2HCl at 0 to 5 Celsius. Right now? Now we are supposed to come up with this. Right? Come up with this. Right? So that can be produced by NH2 appearing here. Right? Okay, sorry, we have started in NO2, right? So again we need another step, no? Right? So that can be produced by NO2, right, by adding tin, HCl and NaOH and heat, and this can be done by just adding Br2, and this can be done by Conc HNO3 and H2SO4 at 50 Celsius. Right now? That is the conversion. So some things will be discussed at the next lesson as well. So with this we'll wind up at this stage, right? So we'll do some more conversions with the use of benzene ring next day onwards. Until then, goodbye.